All right. All right. I may need to charge my pencil. All right. I may need to charge my pencil. All right. I may need to charge my pencil. All right. Okay. I'm going to. I can see the chat on my phone. I'm at home. We've got the pencil charging on the right. And if I remember, I went ahead and fixed that bug involving the function in the path. Let's see what happens. Okay, so data is being read in now. And there's a different bug. Great. Now we'll fix some stuff. That should have been S64. Point to remove index does not exist. All right, so I totally forget everything that we've been doing. Okay, 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 okay. Woo. Somebody's watching? This is so exciting. I can't tell who's watching, but that is still very fun. Kind stranger, I'm very glad you're here. Okay. So the issue is that we're trying to find the linear interpolation coefficients for the spirit kernel. The W is going to be that array, 3D array of interpolation coefficients. Actually, 4D array, sorry. For each coil, we're going to interpolate from all the data points collected by all the coils except for that particular data point of that particular coil at that location. Okay. Here we are iterating over the coil indices, and that's fine. Note that this can be embarrassingly parallelizable. This is embarrassingly parallelizable, and we'll worry about that later, much later. Okay, so we're going to go through and make the rows of A. And I just don't remember what on earth was happening. So why do we have a divide by minus floor divide by 2 there? And M and N, oh, okay, so they're sizes. M and N are sizes of the auto calibration region. Great. Oh, I see, I see. So this is the index to the center of the auto calibration region in the cropped data, ACR. Yeah, so that's the horizontal index, and this is the vertical index. Great, 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 great. Why did I want that size, though? Why the index into the center? I remember doing some explanation about that. But I thought the explanation that we talked about last time was to get this point to remove index. Boy, oh boy. Jonathan Blow makes streaming look so incredibly easy, let me tell you.
I found this on the web.
Siri just thought I asked for something about John. Oh my goodness, and now Siri's going nuts. Pro toss. Excellent. Thank you, Protost. Okay, so the one thing is I can't tell how many people are watching me. I guess I'll figure that out on another day. Okay, 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 okay. So I seemed to think last time that we were going to have this many equations. Oh, okay. And that's because we're only dealing with where the center of the kernel is inside of the auto-calibration region. The kernel is completely inside the auto-calibration region. Hi, Daniel! I did not know your Twitch name. Thank you for letting me know. And I'm excited you're here to do some MRI. Okay, so that's what that's about. I don't understand why there's only half. Why floor of W size divided by 2? That looks wrong to me right now, so we're going to see if we could just get this thing to run and if that's going to crash stuff later. I think it will, and that'll be good. Then I'll know I was right now, and I was wrong last time. Ha. Okay. So now we're going to go through all the locations in the auto-calibration region that we are going to use to determine the linear system of equations. That's I and J. And I and J now are going to be indices into ACR, which has already been cropped out of the data. This is the point to remove. That, of course, is the value of B for this particular index of equation. Why reminds me of StarCraft, though. Then we remove the point that we needed to remove, and that's A. And that's fine. A is empty here. Well, that's not good. How did that happen? All right, this is taking way too long. In order to speed up development, I'm going to save the K data. Pro tip, you don't need to take the size of something. You can just use the size. Okay. Now I wonder if this will crash. It did. Inconsistent. And this is progress, believe it or not. Like we're actually getting some things done. And I think I know the problem. So these are column vectors, right? So this thinks I want to concatenate column vectors horizontally. I actually wanted to do it vertically. Right. Looks like sub ACR is already vertical, so we don't need to do that. Or maybe we did, I don't know. Oh, right. We needed the transpose, we just didn't need the colon operator. Okay, why is that breaking? Let's find out. So A is size, let's see, 225 by 288. Sub ACR is way larger than that. Forgot to multiply by the number of coils. We, of course, have many more equations. Oh, no. Sorry. Here's where I forgot. Okay. Now is A is 225 by 2311, and SCR is smaller. And why is that? So ACR is 17 by 17 by 8. M and N are both 17. Great. So sub ACR is going to be right, by the way. We want, 1800, 1799 elements. So the question is, why doesn't A have the right number here? It's because we don't want the size of the ACR here. We want the size of the kernel. Do we know that? Yes. Okay, so then the question becomes, what is M and N? M and N were clearly supposed to be the size of the ACR, so we're going to make this W size 1, W size 2. Okay, now I understand why. Oh, I always knew that. Okay, so this is also wrong. Plus W. I was wrong. Sub ACR was not correct. There should be a -1 here. $79, and A is now 225 by 199. Okay, so now I'm not remembering. We had this discussion last time as to whether or not we use the values of the other coils at a given frequency. And I don't see why we wouldn't do that. I don't know what exactly they did in the original Spirit paper, but I don't see why we wouldn't, so I'm going to. This is one of those moments where I thought I'd be making much more progress than I am right now, and that's a bummer. Oh, this is silly, this is silly. This is incorrect. Okay. Would it help if I made this bigger? Does that help? I hope it does. Sub ACR is going to equal ACR J minus floor W size 2 over 2 J plus floor W size 2 over 2 I minus floor W size 2 over 2 I plus floor W size 2 over 2. Okay, Ji, the coefficient Ji is the center location of the kernel in the ACR. It's the index for the center. And so I just needed to subtract this away from the other side. Is that right? Yes, that is. So I is going to be ceiling of W size I over 2. We're assuming W size is odd. So if W size were, let's say, 5, 5 divided by 2 would be 2.5. The ceiling would be 3. Great. The floor would be 2. So 3 minus 2 would give you index of 1, and that is indeed the right index. 3 plus 2 would give you 5, which would be, of course, the last index. Okay, so I think this is right, and this was terribly, terribly, terribly wrong. Now ACR has size 199, and so does A. Look at that. Index exceeds the number of array elements. Index must not exceed 200. What's going on there? Right, the point to remove now. Okay, so this looks like it was terribly wrong too. The point to remove is definitely going to be based on the coil, but it has nothing to do with the size of the ACR. Oh, I see. Yeah, I was very confused the other day. Point to remove index is going to equal J plus I times W size 1 plus, let's see, I think this should be, so if we only had one coil, what would be the point to remove? It would be just that, wouldn't it? J gets, and then if, no, this is also wrong. Right, this is, okay, so right, this is not going to be based on I and J, which is an index into the auto-calibration region, we need the point to remove index is going to be just an index into the sub-ACR, not ACR. And so this value here gets us to the center row. Now we need to add that gets us to the center column. If we make this floor, that's the column before the center column. Well, I feel like I should make these a new variable, like half W size or something. I don't know, it might just be easier to do floor. Okay, so if W size is, let's say, is 7 by 5. So it's got 7 rows and 5 columns. Then this is going to be 3, and this is going to be 2, which is going to give you an index of 6. So that's part of the problem there. So now this is going to be 5, and this is going to be 2. That gives you an index of 10, which gets you past the first two. The first 2 columns. And then this is going to be 4, and that'll get you to the right. So 10 plus 4 is 14, and that will indeed be the index of the set middle number of this. How do I know? 7 times 5 is 35, and 35 divided by 2 is 17. Is that what? Wait, was I wrong? Was I wrong? Could that possibly be? So 5 divided by 2 is 2.5. Floor is 2 times 7 is 14. Okay, so this is going to be 14, and this is going to be 3, so that'll be 17. Great. That's just if we're, but what if we're using more than, what if we're not in the first coil? Then we want to make C minus 1 times W size 2 times W size 1. That gets us past each slice of the ACR, of the sub ACR, to give us the 1D index that we need to remove. And now we made it past. Those conceivably are indeed the linear coefficients. And now we want to put a Now here's the thing. This is not based on I or J at all. And that was the issue. Like it doesn't need to be inside there. So now point to remove index is going to be fine just there. Or it won't, whatever. W coil. W for this coil has 199 elements. The point to remove is between 1 and 199, so that should be fine. Why did that break? Because again, it thinks I'm concatenating vectors horizontally, but I want to concatenate them vertically. There you go. Now W size also needs the number of coils. Pretty tough, pretty tough. 5 times 5 times 8, what is that? 200. How many elements are in W coil? 199. If I pad it with 1, 200. Wait, what? Why is it still 199? You don't need this plus 1 here. Okay. Okay, now it could genuinely be the case that W is the interpolation coefficients. And unless I made a mistake, which of course I never do, we can go on. Now, a reasonable thing to do Okay, this is a bit tough, but I'm going to do it a way, and then we'll see about making it more efficient later. How long does this take? 0.17 seconds. Computers are magic. So the issue is that we're going through and finding the interpolation coefficients for each coil, and we're storing them for all coils. And then now, if I were going to do it this way, the thing to do would be to make another loop here to go through all coils and then use the interpolation coefficients to find the missing data. Is that what I want to do? Alternatively, we could find the interpolation coefficients in here. We only need to store the interpolation coefficients for this particular coil. This is what I'm going to do. Now we've got the interpolation coefficients, and we're going to fill in the missing data. Here. It saves a little bit of memory. I mean, it saves a lot relatively, but it's just a little bit of memory. And then W is going to be, in cache right here. It should be. So let's just keep it there and use it. And then we'll destroy it when we're done. Okay, so what's the thing to do now? I'm going to make a function called apply W. Okay, and then the thing is that to do the optimization, we need not only apply W, but also adjoint. So if NREN is less than 2, if op is not supplied, or the op is no transp, then we'll do the regular thing here. What do we call this? Direct transformation here. And then the adjoint goes here. For real matrices, the adjoint's just the derivative, right? I mean, not the derivative, the transpose. Okay. So what is the direct transformation? Well, it's going to be based on W. Now, this function is going to, like, I forget what this is called. This function, the scope of this function is everything defined in this function and everything outside of it, but within this outer function, MRI recon spirit. So it has access to W. And it's going to use the values of W that are overwritten here. That's fine. Because we're going to do it, we're going to use it here. Apply W will be used here. So we have W, and then the question is what is in. So for this, we're going to go back to using the iPad. Just give me a second. Oh, I didn't understand. Okay. I seem to have broken that. We're going to use the all right, there we go. So what's happening? Just cleaning off some stuff on my iPad screen. Okay. If we had all the data and we were just missing one, then if we had all the data except for the center element, right? If we had this, let's make it a kernel that's 5 by 5. If we had all the data except for this one, we could estimate that one just by applying the convolution kernel W. We could literally convolve W and then look at the result just right here. And that would be the value, right? But of course, we don't have all the data. What do we have? We have some of the data. So if, I don't know. Going back to the problem we're going to minimize, right? This is what we're working on here. Okay, and what I'm thinking about now is this operator. So that spirit operator is actually just the convolution of W. Okay, so that's all we need to do. Now, I'm saying convolution, but it's actually like a vector convolution. So that's going to be a little tricky. So if I let K right, this has all the values. For whatever x is, K has all the Fourier values. If we then apply the spirit kernel to K, that should approximately equal K. Oh, but this is, of course, for the regularization problem, not for spirit. That's okay. I keep making mistakes because it's been a while. We are not doing spirit regularization right now. What we're actually doing is spirit. And in spirit, we don't have all the data, right? We have masked data, and I'm struggling to represent this. If K data is equal to MK, all right, let's scratch that. Suppose K, the actual K, the real Fourier values, are K of the data plus the K estimates. Then K data is going to equal to the sampling mask times K, and K estimate is going to equal to the complement of the sampling mask times K. This is our optimization variable. So in this expression here, I'm thinking of M as a diagonal matrix with ones and zeros along the diagonal, but I'm going to change that. So this is all, let's do it all again. Let M be the matrix such that it is comprised of the rows of the identity matrix that correspond to collected data. Okay, then K is equal to MK data. That's true. No. Sorry. K data is equal to MK. So here K, we'll call it K true. This is the full K vector, all of the Fourier values. And M only gives us some of them, and K data here is just a vector of the Fourier data values that were collected. Great. If we had the correct values of K estimate, so here's the thing. M transpose is a zero filling operation. What do I mean by that? Let's say M is 1, 0, 0, 0, 0, 1, okay? And we're going to multiply it by x, y, z. What comes out is xz, okay? What about M transpose? 1, 0, 0, 0, 0, 1. This is going to multiply xz, sorry. And this becomes z. The transpose 0 wherever data was not collected. So I haven't thought about this for a while, but what we need is a relationship that uses M between K true and K estimate. It's easy to do in code. So like M is, oh boy. So K estimate is equal to M complement times K true. Where here M complement are the rows, is a matrix comprised of the rows of I that are not included in M. And again, this is going to be our optimization variable. So what do we want? Minimize if the spirit kernel were accurate, then the spirit kernel applied to K true would be approximately equal to K true. So from here, the spirit kernel minus the identity matrix applied to M transpose K data plus M complement transpose K estimate should approximately be equal to 0. And so for spirit, we're going to minimize the L2 norm. Remember, K estimate now is our optimization variable. We can minimize the L2 norm of that. Okay, so this is minimize K estimate of the L2 norm of A K estimate minus B, where A is equal to the spirit minus I M complement transpose, and B is equal to spirit minus I M transpose K data. And then we can use LSQR to solve this. Okay. So this first one, apply W. This W is what I've been calling the spirit kernel in my notes. So like I say, we've been claiming that this is a convolution, but it's not quite right. Why? Because each Fourier frequency actually collects data from each coil. So each frequency corresponds to a vector of data. So if we had a function called com2d, I don't know. Look at that, com2. Okay, so maybe we could use com2. We're not going to, but maybe we could. I wonder what the boundary conditions are for com2. We're also not going to worry about that. So here, what are we going to apply? We're going to apply the convolution to between in We're taking the convolution of N and W for each coil, and then we're summing the results. That is, we're doing the dot product, which is exactly what we expected. We padded here. We put this 0 here so that we could just call conv2 here. That's why we did that. I think this is complaining because apply W is not used, and that's fine. Now, this is my dworklib library on my computer. I need to take a break, apparently. Natalie? Hello?
Hello?
Yeah. My wife asked me to get the shrimp out of the freezer, which of course I'm happy to do. I will be right back. All right. This is some professional streaming going on here. I'm certain it's only a matter of time before I have like a gazillion followers with exciting stuff like this. Okay, so I have here in my own MATLAB function a circular convolution operator, but then I did something wrong because I've got circconv new, and apparently I've got some other functions that I've changed. So get status. I'm wondering if I changed crop data as a function of, or during this development. It's a very minor change. Let's add that. All right, one less thing to do. But now we've got this circconv. This looks close to what I wanted, but it also looks like it was confused, and I think it'll be easier. What if k is smaller? Yeah, okay, this looks good. we'll just use that. I don't know. Here's what I'm going to do. For some reason, I have circ_com and circ_com2. I've had these things for ever, knowing that one day I would need to deal with it. Never have. Today's the day. Okay. We are going to take the convolution of two matrices, A and B, and it's going to be circular convolution. So circular padding is the boundary conditions. Not really boundary conditions, but it's just circular padding. Actually, it's just circular convolution. The origin of in array is the first element. I have no idea what that means, like none, clueless. Oh. I was thinking this would happen like with arrays of arbitrary dimensions. Let's take the circular convolution of A and capital K. Since we're doing it today, I still get to copyright it in 2024. That is amazing. Okay. Why did it think A was defined? I'm going to keep this. And the rest I'm going to destroy. We're only going to need it in 2 dimensions for right now. So that's all I'm going to do right now. Okay. The direct transformation for these 2-dimensional things is take the FFT2, pad A. This is the convolution theorem now. You multiply it times the FFT2 of pad K, and then you take the IFFT2 of that. That's it. Now, I don't exactly know what I mean by I just realized this. I don't know what I mean by the transformation. I know what the adjoint is of the circular convolution of K, right? Like a linear transformation accepts a vector as input, but here we've got two vectors as input, two matrices actually, which are actually vectors in a vector space. And now C is not defined because I'm still way back here. Usage seems to work. That's always good. It's always good to know how to use something, even though that thing's not done or doesn't work. Okay. This is pretty tough, honestly. I like having a two-dimensional thing, a two-dimensional circular convolution. I'll show you why. That's going to get rid of that for loop here. That was my beautiful daughter. Consider a function of k that is equal to a similarly convolved with k. By the convolution theorem, this equals the inverse FFT of the FFT of A times the pointwise or Hadamard product of the FFT of K. And that is indeed a linear transformation. So what is the adjoint? Let's look it up. It's circular cross correlation. That would be amazing. I'm wondering, I think though that it's assuming real vectors there. Circular convolution and overview. I see, it's a chapter in a book. Okay. Circular convolution. Let's say A and K were vectors, okay? For the sake of argument, we're going to make K 5 long. And here goes K3, K2, K1, K5, K4, and the rest are 0. For the next row, you shift it over. So this is a Toeplitz matrix, I think it's called. This should be K5. That's K4. We'll do one more row just so you get it. Oops. Okay. The adjoint of this thing is you take its transpose and you conjugate it. Conjugate transpose, right? So what is the conjugate transpose of this? I'm using bar here to represent conjugate. Conjugate. 1 conjugate, K4 conjugate. Now here goes K4 conjugate, K3 conjugate, K2 conjugate, I see, so it is just cross correlation of the conjugate. Okay. Oops. I wonder if you could do flip in multiple dimensions at once. Nope. It's got to be a scalar. That's fine. I could just call this function again. Instead, here's what I'm going to do. Okay, so what's going on here? Why is it giving me errors? This statement and possibly others cannot be reached. Oh. Right. Okay, I am assuming that the origin is in the middle of the K kernel and the origin is in the middle of the A kernel. So that when we pad them, the center location is the origin. So I'm going to flip the pad K. I wonder if that does it. I'm going to see if this circular convolution 2 is, if the adjoint operation is indeed the adjoint of the direct operation, and if so, that's probably going to be the end for today. Circ convolution is already in test worklib. I don't know what the issue was with that code that I thought I needed to redo it, but it doesn't matter. I'm going to make them complex. Conv AK is equals circ com2 AK. So this is just me adding a test.
Hi, Daddy.
Hey, beautiful girl.
Mom didn't buy enough shrimp. She's gonna have to go back to the store. I'll be left at home with you.
Wonderful.
I'll leave you alone since you're.
Well, my family's home, and obviously this is going to be a distraction, so I think I'm just going to leave it here for now. I might set up this test off stream. Just a minute, please. Check adjoint is another function in my TorqueLib MATLAB library, sorry. Too many input arguments to circ column. What line? 181. 181. This should be, of course, circ column 2. Oh, right. This is not a parameter, a named parameter. This is just a regular anonymous parameter or something, whatever they're called. Undefined conjugate. Okay. Is it conj? Yes, it is. It's running, but the test failed. I wonder where flip considers the origin to be. Not sure that matters. Like flip 1, 2, 3, 4, 4, 3, 2, 1, right. Flip 1, 2, 3, 4, 5. That's going to be 1, 2, 3, 4, 5, of course. No, but see, the issue is, I would have thought the origin was here. That's where the origin is. Like, that's what FFT shift considers the origin to be. See? So there's a mismatch there. So I got a couple of ways I can go. I can either make my own flip. Or I could flip with a circular shift when it's even. That might be the right answer. Anyways, I think I'm going to have to do that later. Thank you, everyone, for participating today. I'm going to call that the end of the stream.